Let's take a look at this question from Larson's calculus. So we're given the equations of the movement of two different ants. So there's x over here and there's this one. And they're asking us to find a few different things. The first one is the distance between the two insects at time t equals 0. So this is actually pretty straightforward. We're given parametric equations at in t, and we're given the value of t that we need to plug in. So let's just find the points, right? So this is ant 1. Let's call it ant 1. Its location is going to be, if you just plug in 0, you can see it's going to be 6, 8, 3. For ant 2, same exact idea. You just plug in 0 everywhere. And so the first one is going to be 1. The second one will be 2. The z coordinate will also be 2. Now all you have to do is use the distance formula between these. So make sure you get the signs right. 6 minus 1 is 5, so square that. 8 minus 2 is 6, so square that. 3 minus 2 is 1, so square that. 25 plus 36 plus 1, I think that's 62. So it's going to be the square root of this, which is the square root of 62. So this is part A. Let's move on to part B. And we're not actually going to use any graphing utility for this. That's a little bit too difficult. Like, I'm not going to do that. But we can still write an equation, right? We can use a general equation and try to do this on our own. So the general equation for the distance, just like we did this here with t equals 0, we can do it without taking a particular value of t. So we can literally just do the position of ant 1 at any time t minus the position of ant 2 at the same time t, and then find an expression for that. And it's not that difficult. So it's going to be a big square root, but we're going to do it anyway. So this is the square root. We have 6 plus t minus 1 plus t. That's going to be the change. That's going to be the difference in the x coordinates. And then in the y coordinates, it's going to be 8 minus t minus 2 plus t. And then in the z coordinates, it's going to be 3 plus t minus 2t. So let's simplify this. 6 plus t minus 1 minus t is just going to be 5. So that's nice. That also makes sense because that's what we got in the first part. So at least we know that we didn't do something wrong there. Okay, I'll make it a little smaller. So that's 5 squared plus, what do we get over here? We get 8 minus t minus 2. So that gives you 6. And then you have minus t and minus 2. So 6 minus 2t squared. And then what's your third one going to be? It's going to be 3 plus t minus 2t. So that's just 3 minus t squared. Again, not too bad at all. If anything, this is actually nice because this is going to be 4 times 3 minus t whole squared, right? We know that because it's going to be, it's 2 times 3 minus t whole squared. So the 2 squared will come out as a 4. So when you add this onto it, this is just 5 times 3 minus t squared. You're also adding a 25 in front, right? Because you're doing that, we can take out a 5 from everything. Okay, so I'll rewrite it so you can see clearly, but it's basically like this. Okay, and this is actually very nice and easy to work with. I was thinking before I solved the question, I haven't solved it yet. This is my first time doing it, but I thought that we might get something messy, and then we'd have to like find the minimum and maximum distances, right? For part B, we need to see how close to the insects get. But we can actually very clearly see that, right? To minimize this, well, think about it. 3 minus t whole squared. This is greater than or equal to 0. So the closest the ants will ever get is when 3 minus t whole squared is equal to 0, which is at time equals 3. So we know that right away. And then once that is 0, 5 times 3 minus t whole squared will be 0. So it's just the square root of 5 squared, which is 5. I don't know what units are using. Let's check. It's in inches, so it's going to be 5 inches after 3 minutes. That's the time interval that they're giving. Using the graph. Okay, so we don't need to really use the graph, but we can predict just based on this as time increases. So just think about it, right? The 5 square never changes. That's going to be like a fixed thing. And when you're going from t, so t is going to start at 0, we can predict, and it goes until 3. So at this point, like from here, the distance is decreasing because 3 minus t whole squared is decreasing, right? You go from negative 3 squared, which is 9, all the way down to 0. But then anywhere after that, so from 3 until t until, and I think this should just be an open bracket actually. So it doesn't really matter, but it should be an open bracket, I think. from 3 is less than t until infinity, like until whenever, the distance is going to be increasing. So the minimum distance that you get, again, it makes sense. It's going to be right at the middle of these two things when time is equal to 3 minutes, and the minimum distance is going to be 5 inches. So it's a very simple question in the end. You just have to do the work, and we're lucky that this looks like a long and difficult expression, right? Like things get very, very messy with that. Not very messy, like there's still a limit, right? The worst it could be is a quadratic, and then we'd have to find potentially very messy roots of that quadratic. But over here, it's like very nice and easy for us. We've got it all in just one term. It's a perfect square right in front of us over there. So very nice question, I think. I think these are the answers. We didn't do the graphing part, but I think you get the idea, right? The distance will be it'll be decreasing, and then it'll be increasing after that. From 0 to 3 it'll be decreasing, 3 to 10 it'll be increasing, and then yeah, same conclusions about the distance. So that's it for this question. I hope you enjoyed and learned something new. Thanks so much for watching.